Today's lesson is linear versus nonlinear functions, and so by the end of the lesson, you should be able to say that I can represent mathematical relationships using graphs. And so to begin, we have a warm-up, and we need to write a linear equation to describe the image. And so the first thing I notice in each image is that these top three and bottom three blocks never change. It's just whatever's in the middle. And so that's what I'm going to write my equation around. I'm going to say that y equals something plus those 6 blocks, because those 6 blocks are our constant. And if we look at it, in figure 1, we have 1 block. In figure 2, we have 2 blocks. In figure 3, we have 3 blocks. And so we could just say that it's n plus 6. 1 block plus 6, 2 blocks plus 6, 3 blocks plus 6. And the next one, we would have 4 blocks in the middle, and so on. And so right there, we have an equation. And so a review from the other day is, what does it mean if something's linear? And remember, linear means a straight line. We're looking for a straight line and a constant rate of change, or a constant slope. And so just by looking at the graphs, we need to determine if the function is linear or nonlinear. Notice straight lines for these top two, they're linear. And then bottom two both have curved lines of some kind, so they're nonlinear. Next, we're asked if portions of the graph model below could be represented as a linear function. And they actually could. So yes, they can. And it's because notice that even though if we follow this is a nonlinear graph, what happens if we look at just this bottom part? Oh, that's linear. And what about just this top portion? We could make that a linear graph. We could make just this middle linear. And so any of the straight portions, so any straight portion can be represented as linear. So even though the graph as a whole is nonlinear, there are bits and pieces that could be a linear function. And so if you notice here, this one shows you possible problems that could happen. So if you're given just this portion of the graph that I made orange, you don't really know what's going to happen, so you assume it's going to be linear. And so this is what you would predict. However, if the graph is actually nonlinear, like I show here in red, this curved line, then your prediction, the prediction is way off, because in actuality you're way up here with your output or your values for y. And so we need to make sure that when we look at graphs, we not only look to see if they're linear or nonlinear, but we also take note of that in our predictions. Is it a nonlinear prediction or a linear prediction? And so in this next graph, we have scatter plots. And what you need to do is you need to figure out if you would draw a line in here. Would it become linear, a nonlinear, or would it be neither? Could you make the line at all? So looking at it, I would draw a line somewhere right through those dots. I hit most of them. They're equally spaced from my line, and so this would be linear. Go ahead and complete B, C, D, E, and F, and see what you get. And so if you look at my answers, we have B and F were both linear. C and D were nonlinear because they're curved. And then if you look at E, it's neither, because the dots are everywhere. There's no way to figure out if they're upward or downward or whatever. Straight line, curved line. There's no pattern at all, and so that's considered neither. And so now looking at a table alone, we need to figure out if a graph is linear or nonlinear. And then we need to write a rule. And so because we are dealing with functions, when we write our rule, remember our input is x, but now output is function notation, so we have f of x, x, f of x. So rather than using y's, we're going to now start using f of x because it is function. So when we write the rule down here, we're going to have f of x and f of x instead of a y. So first things first, if we look at it, we need to figure out if it's linear or nonlinear and write a rule. So let's figure out our rate of change. Plus 9, plus 9, plus 9, up by 2, up by 2, up by 2. 9 over 2, 9 over 2, 9 over 3, they're all constant. And so we know that our slope, or the rate of change, is 9/2 x plus. Now we need to also figure out our y-intercept. So we need to figure out if we would go all the way back to 0, what would our y be? So we know if we went back to 1, we would minus 9, and we would get 10. And now we need to go 1 back. So we actually need to minus 4.5. And we're going to get 5.5. So 5.5 is 5 1/2, which is 11 halves. And there we go. Also, we have another one on the other side. We have our output. We need to figure out if it's linear or nonlinear. If it's linear, we need to write the equation. So go ahead and try it on your own. And when we look at our rate of change, our input was always going down by 2, but our output was not going down by the same thing. And so we can tell that it's just nonlinear right away. And we are not going to worry about writing the function quite yet. Go ahead and try this one on your own. And remember, independent variable is our x, dependent is the y, which is now f of x since we are working with functions. Notice when looking at it, our rate of change is not constant, and so it is clearly a nonlinear function. On the next slide, we're going to identify from our ordered pairs if it's linear or nonlinear. The easiest way I think to do this is make our own table. X, Y, negative 2, 7, negative 1, 5, 0, 3, 1, 1, 2, 2, 3, 0. And from there, go ahead and see if it's linear or nonlinear and write the rule if it is linear, but remember our rule starts with f of x now. Go ahead and try it on your own. And notice when you look at the rate of change for all points, you can't just do the first few, it is relatively constant until we get this one boxed in purple, which makes it nonlinear, because that's going to give you a bump in your graph, and then it's just nonlinear anymore. It's no longer a straight line. Go ahead and just try these points completely on your own. Determine if it's linear or nonlinear. If it's linear, write your function, which is, remember, f of x equals your mx plus b. Go ahead and see what happens. Notice that our x's are going up constantly by adding 1. However, on the y side, or the f of x side, it's like a total mess. They're going down, they're going up. It is definitely nonlinear. And last but not least, we need to write a rule given the ordered pairs, table, or situation. So, this story problem says that on the first day of work you get 1 penny. On the second day of work you get paid 2 pennies, or 2 cents. On the third day of work he pays you 3 pennies, and so on. Now continue the sentence, giving the logical reason for the next 5 days of work. So would you get 3 cents, then something, or would you get 4 cents, then 7 cents, then something, 4, then 8, then what? And so in each of the 3 situations, what does he owe you after 2 weeks of work? So in this first situation, you get 1 on the first day, 2 on the second, 3 on the first, 4 on the fourth, and so on. The next one you get 1, then 2, then 4, then 7, so on. And in the last situation you get 1, 2, 4, 8, and so on. And then in situation A, how much would he owe you after 2 weeks? In B, and in C. And that's what we need to figure out. So you need to find the pattern and figure out what you would get for 14 days. notice that in situation A you get 14 cents, in B you get 78 cents, and in C you get 16,384 cents because of how they're increasing. And so if I was going to have my boss pay me, I would like to get paid in situation C personally. But did you figure out the same answers?